Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at proton NMR spectroscopy. It is not the easiest of topics, so I'd like you to just stick with it and keep practicing. But we'll have a go. So can we start? So open up your booklets and we'll get going. So proton NMR spectroscopy. There are two different spectrums that can be produced for proton NMR. One is low resolution and one is high resolution. So we're going to go through both of them and talk about the differences. Okay, but first a bit of background. So this type of spectroscopy relies on the magnetic properties of the hydrogen-1 isotope. The key points to note are as follows. So the number of peaks tells us the number of different hydrogen, I'll put chemical or proton environments. You'll see them all described as this. So I'll probably interchange between hydrogen and proton environments. Okay, means all the same thing. E.g., so this is a spectrum that I've drawn. In your exams or on the internet, you'll see slightly better drawings than mine. How many peaks do we have? Well, we have 1, 2, and 3. So there are 3 peaks. Therefore, there are 3 different hydrogen environments. Okay, and all of these examples now are low res spectrum. So this is a low res spectrum. Okay, next one. So the area under the peaks tells us the ratio between the different proton environments. This is often shown on the spectrum using an integration trace, and often is seen as a number in brackets next to a peak, e.g. in here. So I'll just write low res NMR. Okay, so this is exactly the same spectrum, but I've added these numbers here. Okay, 1, 2, and 3 next to each peak. This tells us the ratio of hydrogens in each of these different hydrogen environments. So we would write our ratio as 1 to 2 to 3. Now a just means the number of hydrogens in a proton environment. So in this hydrogen environment, we would have 1 hydrogen atom, this 2 hydrogen atoms, 3 hydrogen atoms, usually. Okay, so next, the chemical shift values tells us what hydrogen each hydrogen belongs to, what different environments each hydrogen belongs to. So what type of hydrogen environments they belong to. So I've just I've just scanned this. So this is one type of chemical shift or data that you will see about proton NMR. It may be in different forms, but it gives basically the same information. So we've got our parts per million down here, and here are different hydrogen groups, and depending on what they are attached to, they will shift down. This is explained in more detail in another video, so if you're unsure about chemical shift, watch that. Okay, so again, I've got my same example, and I can see that the first peak, which has a ratio, probably 1 hydrogen in, is between 12 and 10. So if I look at my chemical shift, it could be this one here. So it's more than likely to be C double bond OH, which fits with our number of hydrogen because we only have one hydrogen. Okay, so probably this one. This one is between 2 and 4, so if we have a look here, well, 3 and 4 maybe, or 2 and 4. What shall we choose? Let's say it is between 2 and 4. So we'll choose this one, so it's between 2 and 3. Yeah, it probably is between 2 and 3. As you can tell, it is quite hard to tell on some of them. So you'll usually get more information on in a question if it's slightly ambiguous. So we will say that this is C double bond O here, and my CH next to it. So this one. And it says that there's 2 hydrogens in, so I can put that on. Okay, this one's a bit easier. So this represents anything which is furthest to the right is probably a HCr. Okay, we know that it's got 3 hydrogens in, probably, so more than likely looks like this. Okay, now I'm going quite fast, but these are all different hydrogen environments within the same molecule. So I can now put these together. So the actual molecule will probably look like this. So my CH3 here, which is attached to an R group, so that means a carbon, which is my CH2, which is attached to a C double bond O, which is the same C double bond O here, and my OH group here. Okay, so it is helpful to keep practicing these. So have a look at this again and see if you can figure out which proton is in which hydrogen environment. Okay, so moving on. So this is only in high resolution NMR. However, we get something else that happens in high resolution NMR, and this is the splitting pattern of a peak. Gives us information on how many hydrogens are attached to the neighboring carbon atom, e.g., and I'm just going to take one of these peaks, e.g., so a splitting pattern, e.g., is in my low resolution NMR, my peak would look like a singlet. However, in my high resolution NMR, maybe it splits further into something that looks like this. Don't worry too much about that. We're going to go through it in more detail later on. Okay, so maybe we should just write here low res and high resolution. Okay, so splitting patterns can be worked out using the n+1 rule, and we'll come back to this later. Okay, firstly though, so equivalent hydrogen atoms. So hydrogen atoms attached to the same carbon are said to be equivalent. So they are said to be in the same proton environment. Okay. Equivalent hydrogen atoms have no effect on each other, so that one hydrogen atom in a CH2 group doesn't cause any splitting in the spectrum of the other one. E.g., so we have just said that hydrogens attached to the same carbon are equivalent, so we just get one peak. So this would be one peak on the NMR spectrum and one hydrogen environment. if I have another carbon attached to it, this would be another proton environment. So in this example, there are two proton environments, therefore two peaks on the NMR spectrum. And this is only example. Obviously, this isn't a full organic molecule. Okay. So, but hydrogen atoms on neighboring carbon atoms can also be equivalent if they are in exactly the same position. Often, usually mirrored. Okay, for example, and it makes more sense as we do an example. I want you to have a go at drawing the displayed formula of 1,2-dibromoethane. Okay, so I'm sure everyone's managed to do this. Now, because this molecule, we could say it's symmetrical or is mirrored, even though we have two carbon atoms, all of these hydrogens are in the same proton environment. If you look at the end of the molecule, I have one bromine here and one bromine here. So it's the same proton environment. Therefore, on my NMR spectrum, this molecule would show one peak in proton NMR. However, if one atom is changed in the molecule, the proton environments or hydrogen environments may no longer be equivalent. Okay, your turn again. Draw the displayed formula of 1-bromo-2-iodoethane. Okay, so in this example, we've changed the ends of the molecule. So we've changed one of the bromines for an iodine. This means that this molecule is not mirrored and is not exactly the same on either side. Therefore, these hydrogens on this carbon will be in a different group or a different environment to these ones. So we have two different environments. As the molecule is now different on either side because we've changed one of the bromines. So this molecule would show two peaks in proton NMR. Okay, right, moving on. So, low resolution NMR. So the spectrum produced by this resolution does not give us any information about hydrogens on adjacent carbon atoms. That will become more important later on. The integration trace measures the area under the peak. This tells us the ratio of how many hydrogens are in each different chemical environment. What we've said earlier, just to repeat. We can use the chemical shift values to identify the different chemical environments for the protons. Again, just to repeat. So, I want you to have a go at this. I would probably suggest you doing this in pencil to begin with, or on a scrap piece of paper, okay? So an organic compound was known to be one of the following. Use its low resolution NMR spectrum to decide which it is. So it could either be propanoic acid, or methyloethanoate, or ethyl methanoate. And I've given you the structures as well. Here is the low resolution NMR. Okay, so we'll have a look at the questions. So you'll need to answer how many different chemical environments for hydrogen atoms are there. So you need to look at your NMR. I will give you a hint. Which molecule will this eliminate? Okay. Next question. What would be the ratio of these environments, so the number of hydrogen atoms in the environment? And how can we identify the compound from the chemical shift values? Okay, right, have a go at this and then we'll go through it together. Okay, actually for this one, we'll go through each question together. So I'll only go through question 1 to begin with. So how many different chemical environments for hydrogen atoms are there? Well, there are 3 because there are 3 different peaks. So if we go back up to our structures, we can eliminate one already, and we can eliminate methyl ethanoate because this only has 2 different proton environments. So 1, 2. Therefore, it would only show 2 peaks. The other 2 would have 3 different. So 1, 2, 3, and 1, 2, and 3. So I still don't know whether it's propanoic acid or ethyl methanoate. We can do this one together, I think. So what would be the ratio of these environments when I look at my integration trace number? So it would be 1 to 2 to 3, which probably gives me the number of atoms in these different proton environments. And how can we identify the compound from the chemical shift values? Okay, well, I'll give you a couple of minutes to figure that out yourself. Okay, I hope you've had a go at it, so we'll go through it. So I need to look at my chemical shift values now. So between 10 and 9, and it's got 1 on it, if I go up, between 10 and 9, it's probably going to be my carbonyl CO, C double bond O, and H coming off. So this is more than likely to be a COH. This is round about 2, and I'll quickly go back up. Sorry, it's round about, it's round about 2 and 3, I think. Let's go back down. Sorry. No, so it's round about 4, apologies. So it's round about 4. So that changes my mind. So if I go back up, it would probably be my HCO bonds because the HC, C double bond O would be slightly below. So I think this is now my HCO, and I know there's 2 in there, so I can just write them on. I've written my 1 on here. This is near 1, so this is going to be my RCH, and I know there's 3 attached. Okay, so now I can write this down here. So I know, how can we identify the compound from the chemical shift values? So the chemical shift at around 10 would be my C double bond H. The one around 4 ppm is going to be my CH2O, and the one around 1 ppm is going to be my CH attached together. I can now attach these together, so I will start with my CH3. Now I know this R group is an R group, so it's got to be attached to a carbon with hydrogen, so it will be this one next to my oxygen, and finally at the end I would have my C double bond OH. So if I go back up, let's see if this has worked. Yes, it has, so this must be ethyl methanoate. Okay, right, so moving on. So identifying a compound from number of peaks. Right, so back to you again. So draw the isomers of the carbonyl containing compounds that have the molecular formula C3H6O. Determine how you could tell how you can identify these two molecules solely from number of peaks in a low resolution NMR spectrum. Oh, right, okay, so I'll give you 5 minutes to have a go at this. Okay, I'm sure you've figured this out. So in my propanone, these hydrogens are equivalent to my methyls on the other side. So these are equivalent, so A and A. Therefore, I'm only going to see one peak because they are both equivalent. For my propanal, all of my hydrogen environments are different, so A, B and C, therefore 3 peaks. So just from looking at my peak numbers, I will be able to tell which the spectrum is, whether it's 1 peak, which will be propanone. If it has 3 peaks, it would be propanal. Okay, so how many peaks would there be in the low resolution NMR spectrum of the following compound, and what would be the ratio of the areas under the peaks? Okay, I'll give you another 5 minutes to work this one out. Okay, I'm sure you've managed to work this one out. So I've labelled it for you, and we can see that our CH3s, again our methyls, so the hydrogens in this are all equivalent. So this would be one proton environment. My CH2 would be another proton environment, and my OH at the end of my carboxylic group would be another environment. Therefore, we would have 3 peaks. Our ratio will be in our first proton environment 369, in our second 2, and in our third 1. So our ratio would be 9:2 to 1. Right, so back to you. So we've got another question here. So answer the following question. So the low resolution proton NMR of a compound with the molecular formula C4H8O2 is shown below. Identify a suitable structure and provide reasoning for your answer. Okay, I'll give you probably 15 minutes to have a go at doing this. Okay, hope you managed to work this out. So, sure you did the first part anyway. So, how many different chemical environments are there? Well, there are 3 because there are 3 different peaks. The ratio of different what information does the integration trace tell us? It tells us the ratio of different proton environments. So 3 to 2 to 3. And how can we deduce the structure from the chemical shift values? Right, so you had to use your data booklet. So I would suggest that the peak near 4 would be CO. I know there's 3 on it, so it's probably got 3 hydrogens, so it looks like this. The peak between 2 and 3 is probably C double bond O with my carbons attached, so and it has 2, so it will be CH2. And the one way down is probably my H, my CH3 attached to the R. Okay, so I tried to make it a bit easier when I've been drawing it out. So this is what it would look like, and then we need to add it together. So how can we deduce the structure from the chemical shift values? Well, this would be at my 4 ppm. It would attach to the one at 3 ppm, which would then attach to my CH3. So this would be my organic structure. And a lot of students get confused about this R group here. So this R group is basically my group at C double bond O CH2. Okay, yeah, so it's attached to carbons and hydrogens, so here. Okay, so if I was just going to write this out, just so you can see the other way around, you probably realise it's an ester, and we would call this, what would we call it? Methyl propanoate. Okay, hope that's a little bit clearer now. Okay, so moving on. So high resolution NMR. So high resolution NMR gives us additional information on the type of hydrogen environments. The peak can be split dependent on the number of hydrogens on the adjacent carbon atom. And this is due to something called a spin-spin coupling. Now, I'm not really going to go through this very much because it's pretty much background knowledge. You just need to be able to interpret these high-res NMR spectrum. So spin-spin coupling. In a high-resolution NMR spectrum, the signal is split into a distinctive pattern. The splitting is called spin-spin coupling and is caused by the interaction between protons on adjacent carbon atoms. So the splitting pattern can be used to find the number of protons on an adjacent carbon atom, which means next to. The pattern is predicted using the n+1 rule. This rule states that for n protons on an adjacent carbon, the number of peaks in a splitting pattern equals n+1. The actual ratio of peak areas in the splitting pattern is related to Pascal's triangle as shown below. Okay, so you need to know the names of these splitting patterns. So a single peak is called a singlet. And that's what you have been seeing on your low res, so it would look like this. A double peak is called a doublet. And a doublet will look something like this. A triplet would look like this. A quartet would look like this. And a multiplet, well, there are different types of multiplet, but I'll do one, will look something like this. And when we say a multiplet, really what we're saying is more than 4. So it's split more than 4 times, okay? And you don't need to go into any more detail than that for this level of study. Okay, so common combinations in a spectrum. I would like you to name what these are and then I will go through them with you, okay? So for example, what is the name of this and this one? Okay, so I've named them. So this is a triplet, this is a quartet, this is a doublet, this is a triplet, this is a doublet, and this is a multiplet. Okay, so if you see these on an NMR spectrum, they don't have to be next to each other, but if they're on the same one, it usually gives you some indication of the structure of the organic compound. E.g., so according to our n+1 rule, a peak will split to n+1 depending on what the adjacent carbon, how many hydrogens are on the adjacent carbon. E.g., so if I have something split into a triplet and a quartet, it probably means that I have a CH3 and on the next one I have a CH2 next to each other. 2 different environments, so I get 2 peaks and the splitting pattern will be distinctive in NMR. Right, so this is where it gets slightly confusing. So if I look at my CH3 peak, okay, so this, according to the n+1 rule, is next to a carbon with 2 hydrogens on it. So this peak would split into a triplet because it's next to a carbon with 2 hydrogens on it. My proton environment with 2 hydrogens is next to a carbon with 3 hydrogens on it. Therefore, according to the n+1 rule, it will split into a quartet. So in this example, my quartet would be a CH2 and my triplet would be a CH3. Okay, this is where students start to get confused a little bit. So you have to remember that you're looking at the adjacent carbon. Okay, the adjacent carbon. Okay, right, so I'd like you to have a go at trying to do the next to yourself. Okay, I think we'll do the last one together actually. So in this example, I hope you managed to do this one. So I've got a doublet and a triplet. So if I have a doublet and a triplet, I must have a CH and a CH2. Remember, if I look at my my CH, it is next to a CH2, so it will split as to a triplet. My CH2 group is next to a CH, therefore it will split into a doublet. Okay, I hope you're starting to get the hang of it. I know it is quite difficult. So if I've got a doublet and a multiplet together, it probably means, well, if I've got a doublet, I know that there must be a CH somewhere. If I've got a multiplet, that means that I have a carbon with one hydrogen next to a carbon that has lots of protons in a neighbouring carbon. Now I know that I can't have more than 3 hydrogens on one carbon. Therefore, to get a multiplet, I must have some equivalent proton environments. So here I have a structure. Okay, so let's work through it. So my CH is next to 2 A and A. It's next to it's next to 1 proton environment because these 2 methyls are equivalent. So we can write are equivalent. Therefore my CH is going to split into my multiplet. So this will be my CH. My equivalent methyls, so remember they're in 1 peak or in 1 proton environment, so it has 1 peak, is next to a carbon with 1 hydrogen, so this will split into my doublet. So in this example, this will be my CH3 times by 2 because it is 1 environment, because CH3s are equivalent. Confused yet? I hope not. I hope you're starting to get it. Okay, so we'll move on. So using the n+1 rule, so the spectrum above, oh sorry, let's change that because it's definitely not above. The spectrum below is a high resolution spectrum of a compound with the molecular formula C4H8O2. What information can you get from this NMR spectrum? Okay, so have a look at the spectrum. It's not my best drawing, I know, and see if you can work out the answers to these questions. Remember, you can now use the splitting patterns, okay? Okay, so let's go through it then. I hope you had a go. So how many different hydrogen environments? Must be 3 because there are 3 peaks. What is the number of hydrogens in each environment? 2 to, whoops, let's see if I write it right. 2 to 3 to 3. So it's probably 2 hydrogens in one environment and 3 hydrogens in the other 2 different environments. What information can we gain from the splitting patterns at the peaks? Well, we know there's a triplet and a quartet, so that probably means there's a CH3 and CH2 in there somewhere, and we also have a singlet as well, so that means we must have a proton environment with no neighbouring carbons, as it's a singlet, it hasn't split. Okay, so I'll now look at my chemical shift values. This is around 4 ppm, parts per million, so it's probably COHH2, This is nearly between 2 and 3, so it's probably C double bond O CH3. And this is my one way down, so it's probably the CH3 attached to my R group. So it looks like this. Okay, I can now add these together. So I start with my R group, which would be CH3. Remember, my R group needs to be next to a C and H, so it's got to be this one, CHO, which goes to my group at 3 ppm, so it would look like this. Okay, so my structure must be, I'm just going to write it round how you usually see it, CH2, CH3. Now we can go back and confirm this. So let's see if it works. What information do we have in the question? Well, we know in the question that it's C4H8O2 is the molecular formula. 1, 2, 3, 4. 2 oxygens, 3, 4, 5, 6, 7, 8. So that's correct. We have a CH3 and CH2 next to each other. That explains my triplet and quartet. My chemical shift values are right. I have a singlet, my CH3 here, which is next to a carbon with no hydrogen, so it shouldn't split. Well, it hasn't. And I then can check my integration traces, which are 2, 3, 3. So that would be 2, 3, 3. So it fits. Okay, right. I know that is quite difficult. Yeah, so I will go away and do some practice on these determining organic structures using high resolution NMR. We do have one last bit to do, okay, so we're going to go through that. It's not quite as complicated as this stuff, you'll be glad to hear. So, identifying OH and NH peaks. So look at your datasheet. Why might it be very difficult to pick out an OH and NH peak by using chemical shift values? So I'll give you 30 seconds just to have a look at your datasheet. Okay, I'm sure you've worked it out that the OH and NH peaks have a really big range. So it's difficult to tell. Okay, but there are some important bits of information that can help you out. So, OH and NH peaks always appear as singlets. Right, so they never split, even if they are next to a carbon with hydrogens on it. Right, that's important. The hydrogen environment next to these two peaks never splits as well. So these two peaks, I mean OH and NH. Okay, so important. So how can we tell the difference between an OH and NH peak and carbon with only one hydrogen on it? Wouldn't they produce a singlet for the splitting pattern of a neighbouring carbon? Yes, they would. So this is why we use something called D2O. Okay, what's happened to my thing? Right, so I'll be back in just a second, as my ink seems to have made a mess of itself. Okay, so I think I've got it fixed. So how can we tell the difference between an OH and NH peak and carbon with only one hydrogen on it? Wouldn't they produce a singlet for the splitting pattern of a neighbouring carbon? Yes, they would. But we can use something called D2O. So the use of D2O. So deuterium is an isotope of hydrogen with one extra neutron. So it would look like this. So we give it the symbol D. Its mass number is 2, proton number 1. Okay, can remove. So D2O can remove an OH or NH peak from a spectrum. This happens because the deuterium atom can replace a hydrogen atom in the OH or NH group. Take, for example, ethanol. Ethanol is weakly acidic. This means it can interact water by this method here. Okay, So all I've done, and you've probably seen this before, is instead of applying H2O, so ethanol is weakly acidic, so it will donate one of its H pluses off the OH group to the water to produce my oxonium ion. So all I've done is taken one of this H's and replaced it with a D2O. The interchange can then occur again by this time with a deuterium atom. So here I'm taking my H2TO plus, it's missing a plus, and it can give back one of the deuterium atoms instead of one of the hydrogen atoms. So deuterium instead of hydrogen rejoins. Okay, so all I've done is taken one H atom out and I've put one deuterium atom in. And deuterium atoms do not produce peaks because they have an even number of nucleons. Right, so this is a very simplified explanation, but it will do, okay? So really you need to know how to use it. So using D2O. So produce a spectrum of a sample normally, add D2O to the sample and produce a second spectrum. The OH or NH peak would disappear off the second spectrum, like magic. Okay, so let's have a go at doing this question. Last one. So an organic molecule has a molecular form of C2H6O. It can be reacted with a carboxylic acid to produce an ester using a concentrated sulfuric acid catalyst. Its high resolution spectrum is shown below. Okay, what information can we give the chemical shift? What could be the structure of the molecule? I reckon you should be able to do this. So have a go at doing this question. Okay, I'm sure you've worked this out. So what information can we get from the splitting pattern on the above spectrum? Well, we can see a triplet and a quartet. So it's probably CH3 and CH2 next to each other. What information can we gain from the chemical shift values? Well, we can use our chemical shift to work out this is probably CH2O. I'd say we don't really know what this one is at the minute. And our third one would be CH3 attached to R. We know that CH3 and CH2 are going to be next to each other. From the question, if I know my organic molecules, if I react carboxylic acid with an alcohol, it's going to produce an ester. It has the molecular formula C2H6O, which probably means it's going to be this structure, CH3CH2OH. If I go back up, now my mysterious one, my mysterious singlet peak is an OH, which fits because it is never split and doesn't split any of the other peaks. So draw the spectrum. You would expect to see if D2O is used as the solvent, is used in the sample. So I've mixed it in. Well, my OH peak, which was here, would disappear. So the OH peak disappears. Okay, why is this useful? Well, once you run the second spectrum, you'll know which one the OH and the NH peak is. Right, I know that was pretty hard work, so I think you deserve a break, and I think I do as well. So again, as always, I hope that was useful. Please go away and practice this. It's definitely not the easiest topic. Okay, right. I will see you next time. Bye-bye.